So we have problem number 2 in advanced classical mechanics practice final exam. So find the curve y of x. X belongs to the interval 0 to L, connecting 0, 0 to L0. That extremizes this functional j of y equaling 0 to L for this integral square root of 1 plus y prime squared dx. Subject to the fixed area constraint, this integral from 0 to L, y of x dx equals a. So for part A, formulate the constrained variational problem. For part B, derive the Euler-Lagrange equation. For part C, show that the extremal curve is an arc of a circle. And part D, explain physically why this result is expected. Okay, so we'll go through this. Calculus of variations with an integral constraint. So this is a variational problem with a fixed area. So we want to extremize this j, this functional j of y, which is equal to this integral from 0 to L, square root of 1 plus y prime squared dx, subject to the integral 0 to L, y of x dx equals a, with y of 0 equals 0 and y of L equals 0. So what we're going to do is we're going to introduce a Lagrange multiplier, lambda, and extremize functional script I of y. Set that equal to 0 to L for that integral, bracket, square root of 1 plus y squared plus lambda y, close bracket dx. So the effective integrand is going to be f of y comma y prime equals square root of 1 plus y prime squared plus lambda y. So our Euler-Lagrange equation is going to be the partial derivative of f with respect to y minus d dx, partial derivative of f with respect to y prime. That's going to be equal to 0. So building on that, what we have here now is the following. This partial derivative here of f with respect to y equals lambda, and partial derivative here of f with respect to y prime equals y prime over the square root of 1 plus, that's y prime squared. Therefore, lambda minus d dx, y prime over square root of 1 plus y prime squared, that equals 0. So what we could do here is d dx, for this y prime over square root of 1 plus y prime squared, that's equal to lambda. Integrating once, y prime over the square root of 1 plus y prime squared, that equals lambda x plus c. So we can let lambda x plus c equals s, then y prime over the square root of 1 plus y prime squared equals s. So now we could go about and solve for y prime. Y prime squared equals s squared over 1 minus s squared. And then taking the square root on both sides, taking the positive value of that, y prime equals s over the square root of 1 minus s squared. And since s equals lambda x plus c, we could say that y prime equals lambda x plus c over the square root of 1 minus the quantity lambda x plus c squared. So we could integrate, and y of x equals negative 1 over lambda times the quantity square root of 1 minus parentheses lambda x plus c, close parentheses, squared, and then on the outside plus d. So square root of 1 minus lambda x plus c squared equals negative lambda times the quantity y minus d. So squaring, we get the following. lambda x plus c, that quantity squared, plus lambda squared times the quantity y minus d squared equals 1. Now if we go ahead and we divide by lambda squared, we wind up with the quantity x plus c over lambda squared plus the quantity y minus d squared equals 1 over lambda squared. Okay, so building on that, what we could say is the following. Oops. So the extremal curve is an arc of a circle, and we could use this formula for circle: x minus x naught squared plus y minus y naught squared equals r sub c squared, where r sub c equals 1 over the absolute value of lambda. So the constants x naught, y naught, r sub c are fixed by the endpoints in the area constraint. And because the endpoints are symmetric, the circular arc is centered on the vertical line x equals L over 2. So convenient form is this: x minus L over 2 squared plus the quantity y minus y naught squared equals r sub c squared. And using y of 0 equals y of L equals 0, we have L over 2 squared plus y naught squared equals r sub c squared. And the area condition for this integral from 0 to L, y of x dx equals a, then determines r sub c or y naught. And we could say here the constants are fixed by the two endpoint conditions plus the area constraint. And to wrap things up here, we could say that physically this is expected because the problem is equivalent to finding a curve of stationary length subject to fixed enclosed area. The classical isoperimetric principle says that constant curvature curves appear in such problems. And in the plane, constant curvature means a circular arc. So the extremal curve is a circular arc, and that is determined by the endpoint and the area constraints. So that's all for problem number 2 of 15. Thank you very much and have a great day.